All right. The last session before lunch was about the coarse graining method, PCCA, that was already mentioned just a few minutes ago by Simon in his talk. And I'm just going to make you familiar with a few more details, what is actually happening in this method. Yeah, PCCA stands for the slightly strange abbreviation, Heron Cluster Analysis. Say a few words about this in just a second. Is, as we already explained, a coarse graining method for Markov state models. So it is a method that can help us go from our original state definition for our Markov state model that likely involves a lot of states that were generated by our clustering of the data to hopefully a much smaller number of macro states, sort of agglomerated states of the original state definition. And these smaller number of states can be used for visualization and interpretation purposes. The goal is to extract the metastable states of the system that we expect to find more or less automatically based on the structure of the dominant eigenvectors. Let us come back to the picture you've already seen a number of times the last 1.5 days. In this simple model system, we have looked at the dominant eigenvectors of the Markov chain, and we have, should we put this? It's not possible?
It's broken.
Oh, it's broken. Okay.
We're going to turn off the light.
Right. We have seen that the dominant eigenvectors of such a system possess this typical sign structure, the structure of being constant, or more or less constant, along the metastable states. What this means is, can you turn this one off as well? No. Okay, thanks. What this means is that the dominant eigenvectors can be expressed as a linear combination of indicator vectors. Yeah? We have identified our metastable states to correspond to these 4 minima here, and we can think of an indicator vector for each of these metastable states. This would simply be a vector which is, let's say for the first one, which attains the value 1, that for all of the states that pertain to minima number 1, and it is 0 everywhere else. And in this way we define 4 of these indicator vectors of the metastable states. That as a consequence, so for example, the second eigenvector could be written as, let's say, -1 times the first indicator vector, -1 times the second indicator vector, +1 times the third one, and +1 times the fourth one. Yeah, so it's a simple linear combination of these indicator vectors. And this is the idea. And we can also exchange roles and say that we expect such indicator vectors to be expressible as linear combinations of the dominant eigenvectors, up to a small error. The error will occur predominantly in these transition regions. This is the formulation that PCCA uses. This is also the reason where the name comes from. People talk about the cluster of dominant eigenvalues and eigenvectors. This is called the Perron cluster. So we use the Perron cluster to perform a cluster analysis. This is why people have come up with this slightly weird name. All right, let's formalize this problem. Let's say that n is the number of states of our original Markov chain, and nc is the number of dominant eigenvalues. That's also the number of metastable states we expect to find. We can compile a matrix of the dominant eigenvectors, just call it X for the rest of this talk. This is a matrix of dimension n times nc. Yeah? So every column of this matrix has n entries, and we have nc dominant eigenvectors. The goal is to find a matrix of membership vectors. I will call this matrix chi. So this is the same dimension, so also n times nc. And each column of this matrix will be interpreted as a membership vector that assigns to every state, every microstate in our original state definition a degree of membership of belonging to this particular macro state. Yeah? In mathematical properties, this can be expressed by demanding, first of all, that all the entries of this chi matrix should be positive. Negative memberships do not make sense. And moreover, if I'm summing up the degrees of membership of a single microstate, yeah, so I is a microstate index, a row index in this matrix, and I'm summing over all the columns, so over all possible microstates, then these degrees of membership should sum up to 1. Right? What you see here is that we are not asking for a strict assignment of every microstate to a single macrostate, but we are asking for a sort of fuzzy assignment. Yeah? It is allowed that a single microstate pertains with, let's say, degree of membership 1/2 to macrostate 1, and degree of membership 1/2 to another macrostate. That's okay. So these two properties they encapsulate what we expect for this matrix chi to hold. It's a slightly weaker formulation than what I originally said. And you can certainly imagine that when people started working on this, the first approach was to aim for a strict assignment. But it soon turned out that this is very susceptible to numerical instabilities and all sorts of problems. And it also makes sense. If we look back at this picture here, then we realize that assigning this particular state here to one of the 2 or one of the 4 macrostates in a strict way doesn't seem to make so much sense, right? It makes much more sense to assign this particular state with, let's say, degree 1/2 to this state, and degree 1/2 to this state. So this formulation seems more suitable than a strict assignment. Okay, do you have any questions up to this point? No. Okay. And the goal was to find the chi, and the chi matrix was supposed to be a linear combination of the dominant eigenvectors. So we can formulate this in this equation. Chi should be equal to the matrix of dominant eigenvectors x times a transformation matrix A. So A is a small matrix of dimension nc times nc, and that transforms the eigenvectors into this membership matrix, plus some error, because we cannot expect this equality to hold exactly. That's the goal. Yes? Yes, it has the same size as the number of columns of x. Yeah? The number of columns of x is the number of dominant eigenvectors. So this is small. Yeah, that's why I said it's a small matrix. So, x is n times nc, and n can be large. Yeah? So it has possibly many rows, but only a few columns. And A has shape nc by nc. So,
Sure.
yeah, it's okay? Good. All right. So this is the equation we try to solve, or the problem we try to solve. And how can we approach this? Up to this point, it can be quickly realized that there are infinitely many solutions to this problem, and many of them don't have any intuitive sense. So before tackling this problem any further, we have to define some optimality criterion for the A. Yeah? And that's what we're going to do next. And the criterion that people have used is based on the idea of defining sort of a coarse-grained dynamics, yeah? And then a simplified dynamics on the space of macro states. Let us first of all observe that it's very simple to restrict a probability density, so a state, a description of the state of the system on the fine space, on the original state space, and it is easy to transform it into a probability vector on the coarse-grained space, on the small space. We can take any probability vector, Pf, which has length n, so it's a probability distribution on the fine space, on the original one, and we can transform it into a probability vector just on the coarse space by simply applying this transformation matrix. can simplify this chi matrix. Because of this partition of unity and positivity property, the result is again a probability vector. So in this way, we can coarse grain state descriptions of the system onto the coarse space. And let us just formally give this chi another name. Let's call it R as for a restriction operator. This restricts density on the fine space to the coarse space. And ideally, it should be possible to find a transition matrix, a small transition matrix, so a transition matrix acting on the coarse-grained space, such that this diagram here commutes. We want to start at a fine density on the original safe space, and we want to arrive at a density on the small space after propagating the system for one step. So for one step of left-hand tau, if tau was the definition used for the definition of the system. And ideally, it shouldn't matter if we first propagate the density Pf on the original space using the original transition matrix T and restrict afterwards, or we first restrict it to the coarse-grained space and then use our coarse-grained transition matrix Tc. This would be great if we could find it. Now, the first approach to do this would be by, well, let's say we simply take the matrix of joint probabilities on the original state space. So T, capital T, was the transition matrix, a matrix of conditional joint probabilities, and we transformed it into a matrix of joint probabilities by multiplying it with pi. Pi is the matrix of stationary distributions. And then we simply coarse-grain this matrix by applying the chi matrix on both sides. So we just apply chi on the left and chi on the right. And the result is a matrix of joint probabilities on the coarse-grained space. Again, because of the properties of chi, this positivity and partition of unity property, this is a valid matrix of joint probabilities. So all the entries are positive and the entire matrix sums up to 1. That's a valid step we can take. And then it's easy to get to a transition matrix. We just renormalize the matrix. We just divide every row by the corresponding row sum. The first suggestion would be to take this matrix, joint probabilities, that we have derived up here, and just multiply it by a diagonal matrix of its row sums to arrive at a transition matrix again. Up to this point, we haven't done anything wrong, and let us just introduce some more notation at this point that helps to interpret this a bit. We've already said that the chi factor down here can be interpreted as restriction, so we use that again. The next part is the t factor, we just leave it unchanged. And we interpret all the rest, this the inverse times chi transpose times pi, all of the remaining factors, as an interpolation operator. We can read it as a matrix that projects a probability density on the coarse space onto a density on the fine space. And in this way, the small matrix here can be read as the sequence of 3 events. First, remember, we propagate densities by multiplying from the left. Just 1 second. So we first interpolate it by projecting it transforming it onto the fine space. Then we use the original propagator and restrict in the end. Basically, we're going this, we are following this path in the diagram. Your question, please.
What is the left chi transpose?
So what's your question? It's this membership matrix
yeah,
again?
Because, well, I was just trying to follow you applied chi to both sides, but those guys are different, right? Or maybe
No, they are the same.
Okay.
So you're just summing up the states with the respective degrees of memberships on both sides to obtain a smaller matrix. Yeah? Okay, so this is how we can read the matrix. But it's quite easy to check that this matrix does not satisfy these commutation relations that we asked for. One way to see this is to remember this matrix here, the chi matrix, was just a transformation of the dominant eigenvectors. So the range of this matrix is just the linear span of the dominant eigenvectors. That means that after the interpolation step, every density can only be contained in the space of dominant eigenvectors. For any other initial probability density, we are losing information. Yeah? If we first restrict and then interpolate again, we definitely lose information if we perform these steps. Now, you can perform a few more transformations and come up with a reduced transition matrix that actually satisfies these commutation relations. And all you need to add is an additional factor, Ra, basically restricting and interpolation, and take the inverse of this matrix. And the rest is unchanged. I think the intuition behind it is that this Ri factor, so first restriction and interpolation, can be read as a bit of an overlap matrix between these agglomerated states. And remember that we have not made a strict assignment here. So somehow these states overlap with each other. And we have to sort of reweight the transition matrix with this overlap matrix. I will show you a reference where all of the details are worked out in the end of the talk. Also, if we were really to perform a strict assignment, then this Ra factor would vanish. It would not vanish, it would be an identity matrix, and it would not play a role. And the original matrix we have suggested would be a valid transition matrix. For now, using this definition, we can obtain a transition matrix on the small space that does satisfy these commutation relations, and it also preserves the dominant spectrum, which is also a very desirable property. Yeah? So we're not changing the essential dynamics of the system on the coarse-grained space. The price to pay for this, however, is that TC is not a real stochastic matrix anymore. It is still a matrix where all the rows sum up to 1, as they should, but negative elements can appear, and also elements greater than 1 in theory. Yeah? So we cannot really interpret it as a stochastic transition matrix between the states anymore. Now we might ask the question, what is it good for? Remember that I told you that if we perform a strict assignment, this factor would be an identity, and we would be using a valid transition matrix that only possesses entries between 0 and 1, and all rows sum up to 1. So what we can try to do now is try to find a soft clustering that is very close to a strict assignment, yeah? Such that this Ri factor here is not exactly an identity, but very close to an identity matrix. And that is exactly the optimality criterion that is used in PCCA. We still try to find a soft or fuzzy assignment of the states, but we try to make it as strict as possible. And that makes sense in view of the metastability structure of the system. We have to expect a few perturbations, but in general, we still expect a rather strict assignment. And if this is possible, if this Ri factor is really very close to an identity matrix, then the deviations from a true stochastic transition matrix shouldn't be too drastic. And this is what is observed quite frequently in practice. So in the end, I already said this, we try to find an assignment such that Ri is close to an identity matrix. So in the end, the objective function to be minimized is basically just NC minus the trace of Ri. The reason for this is, again, I told you the objective is to make Ri close to an identity matrix. Now it can be shown that the trace of Ri is always smaller or equal to NC. And if it really was an identity matrix, then it would be equal to NC. So this function is minimized, subject to all of the constraints that we have imposed previously based on the positivity and partition of unity property, and so on. This is the problem that is internally solved if we make the call to PCCA. I think you have already seen, it's very hard to read, but you've already seen it. If you have extracted your Markov model object, you have this function PCCA that runs the algorithm underneath. You only need to supply the number of metastable states that are desired. And afterwards, you can access the memberships and the metastable distributions and the assignments and so on by just calling these methods. Yes, that's all. Do you have any further questions?